So I've decided to put chapter 12 in before 10 and 11 because in my mind it just makes sense to go from one sample against a hypothesized mean to comparing two samples on some average or mean to comparing paired samples over time. It makes sense to just go into the next question, which would be, well, what if I want more than two samples, so 3 or more samples on some average or mean, which is what we do when we're doing ANOVA. And I really hope you watch the videos, the Khan Academy videos, because it makes clearer than you ever to see it done than for me ever to have read it in a book. So watch that prior to doing this PowerPoint. All right, so let's recap. So remember our flowchart at the end of the last PowerPoint. We have the research question, and we said if we want to describe, we do these descriptive statistics. If we want to compare, and I've altered this a bit, if we want to do relationships or predictions, we're going to talk about that next. So if we want to compare, the first question is, how many groups do we have? If we have one, we need to ask ourselves, is it paired? If it's not, we do the one sample test. If it is paired, we come down here and do the paired samples t-test. And this may not be the greatest flowchart because I get kind of lost in the arrows, but anyway, if we have two samples and they're paired, they're not paired, we do the independent samples t-test. If they are paired, we do the paired samples t-test. Then, if we have 3 groups, we have to ask ourselves, how many independent variables do we have? Do we have 1? If we do, we do the one-way ANOVA. If we have 2 or more, we have the factorial ANOVA. And this section here is what I'm going to talk about today. All right, so an overview of analysis of variance, and it comes from AN analysis, ANOVA is why we call it ANOVA, is a hypothesis testing procedure that is used to evaluate the mean differences between 2 or more treatments or populations. As with all inferential procedures, ANOVA uses sample data as the basis for drawing general conclusions about the population. A major advantage of ANOVA is that it can be used to compare 2 or more treatments or groups. So so far we've been following a T distribution, and now we're following an F distribution, just named after Ronald Fisher, the guy who created this test. You might remember that the Levine's test uses an F distribution. There's a different F distribution for each different pair of degrees of freedom for numerator and denominator. So when we write it out in our APA or AMA format, you write F, and instead of just having one degree of freedom, one parentheses with one set of degrees of freedom, so say you had 20 people in your group, you'd say T of 19. Now we have to do the numerator and then the degrees of freedom for the denominator. And that's because it's a ratio, and it's a ratio of variances. And it's a right-skewed distribution. Values can't be negative. And then the exact shape of this actual distribution depends on the 2 different degrees of freedom. And that's pretty much the most theoretical I'm going to get on you about this. Okay, so let's look at one-way ANOVA. So as you saw in the video, the Khan Academy videos, it's when you have 3 different groups, right? You have population 1, treatment 1, population 2, treatment 2, population 3, treatment 3. This could be the control group and 2 different levels of some treatment, or it could just be 3 different groups, and you want to see if there's a difference among the 3. All right, this is based on the data from the first example, which I'm going to go over. So this hypothesis testing for ANOVA is just like the ones in t-test, right? We do the same thing. We state the null hypothesis that states there's no treatment effect. In an ANOVA with 3 groups, the null could appear as the mean of the first group is equal to the mean of the second group, which is equal to the mean of the third group. The alternative hypothesis states that the population means are not all the same. So the alternate hypothesis, we can write it out now. We could do it with not equal signs like this, but the easiest way to do it is just to use the words. There is at least one mean difference. Now our test statistic is considered the F test, and we look at the variance between the samples and then the variance within the samples. Remember, he was saying the sum of squares between and the sum of squares within, the mean squared between, the mean square within. then we report it with the degrees of freedom of the numerator and the degrees of freedom of the denominator. But the computer will do it for us. So some terminology in the analysis of variance. In ANOVA, the independent variable that designates the groups as being compared is called a factor. The individual conditions or values that make up a factor are called the levels of the factor. A study that combines two factors is called a two-factor design or a factorial design. Okay, so with all statistical tests, we have some assumptions that we need to follow. So that each group is, the first assumption is that each group sample is drawn from a normally distributed population. So we're going to run an explore routine on that. All populations have a common variance. We're going to ask for a Levene's test on that. And then these we just have to assume are done when we get data sets. All samples are drawn independently of each other, and within each sample, the observations are sampled randomly and independently. Okay, so why ANOVA and not just a bunch of t-tests? Couldn't I just run a bunch of t-tests? Well, that's not allowed, or it's highly frowned upon, because as we increase the number of t-tests, we increase the risk of making a type 1 error. Remember those? Those are the mistakes we make when we say that the null hypothesis is false when it is not. It is the incorrect rejection of a true null hypothesis, otherwise known as a false positive. Just think of the picture with the pregnant man. That's the false positive. So we can't, it's not looked well upon to do a bunch of t-tests. So we do this analysis of variance routine. It's very simple to do. You should just have a few more steps. We get an ANOVA source table, and K is the number of groups, and N is the sample size. So our degrees of freedom for the between is K minus 1. So for the example I showed you before, that'd be 3 groups, so that's 2. And then this is the overall sample size, which would be whatever that is, minus 3 for the number of the degrees of freedom for within. So this would be the degrees of freedom of the numerator and the degrees of freedom of the denominator. So mean square between, mean square within, which gives us an F statistic, and we can go look in a table or just look at our output and see if it's if the p-value is small enough to reject the null. All right, so let's look at an example on page 535, example 1. We're comparing children's IQ level and whether or not they had low blood lead levels, medium, or high. So what I did was I took all of these data and I entered them into SPSS. The first group got the label 1, here, low blood level. The second group got the number 2, medium, and then high. All right, so the first thing we're going to do is we're going to check normality. And we're going to go analyze descriptives, explore. We've done this before. Bring our dependent, bring our factor over. Uncheck stem and leaf, check normality plots with tests. And then we get our output, and it says the significance here, none of these are significant, so we say that the data are normally distributed. So what would be our research question for this test? Is there a difference in IQ among children with low, medium, and high blood levels of lead in their blood? And if you were doing something like this, you would have to go and say how you operationalized low, medium, and high. And I got this on it comes from dataset 8 on page 641. I'm not going to go all through that, but it says just briefly, data are measured from children in 2 consecutive years, and the children were living close to a lead smelter. Lead is the blood level group. 1 is equal to low if blood lead levels were less than 40 micrograms per 100 milliliters in both years, medium, et cetera, et cetera, et cetera. So they operationalized what they meant by low, medium, and high, and that's part of what. All right, so we go to our steps for hypothesis testing, and we state the hypotheses. Now, normally we'd say the mean of 1 is equal to the mean of 2 is equal to the mean of 3. And then the alternate is that there is at least one mean difference, but we can say that we can just use words. So the null would be that there is no difference in IQ among children with low, medium, and high levels of lead in their blood. And then the alternate is that there is at least one mean difference among children with low, medium, and high levels of lead in their blood. Step 3 is to calculate the test statistic, which you can see is very convoluted to do it by hand. So we're going to use the computer, and then we'll make our conclusion. So we go into Analyze, Compare Means, Way ANOVA. I bring my dependent list over here, my dependent variable over to the dependent list, and I bring my factor over here. I'm going to click Post Hoc, which means after the fact in Latin, here. And what that means is, okay, we have low, medium, and high. If we get a significant result for our overall test, otherwise known as the omnibus test, then it tells us, yeah, okay, there's a difference, but we don't know if it's between the low and the medium, or the low and the high, or the medium and the high, which is why we are going to do post hoc, after the fact, multiple comparisons. So I click this box, it pops this box up. We have all of these we can do, but we're going to do LSD, which is not the drug. It stands for least significant difference. And we have different, I say this in the SPSS homework as well, there's different kinds. The book mentions Bonferroni, Scheffé, I've learned, Tukey, I've learned, there's a bunch, Duncan's, Dunnett's. There are just a bunch of different kinds. Everybody wanted to have their own multiple comparison with their name on it, so there's a bunch. This one's probably the most liberal in terms of you will find significance if you use this one. This one's, Scheffé is probably the most conservative in that you probably won't find significance unless it's a really big difference. So we're just going to use LSD because it's the easiest one to interpret, which stands for the least significant difference. So what do? And then we go and we click on options, and we want descriptive statistics, homogeneity of variance, that's the Levene's, and then we're going to ask for a means plot. All right, so we check our assumptions. In order to check the assumption of equal variances, I'm just reminding you, we're going to run a Levene's test. Remember, the null is that the variances are equal. The alternate is that the variances are not equal. Because we want equal variances, we don't want to reject the null, so we want a significance of p greater than 0.05. So first, let's look at our descriptives and let's see what we get. So with kids with low blood level, they have IQs of about 102, which is right in the middle of average. IQs are means at 100 with standard deviation typically of 15 or 16. Medium blood levels have IQs a little bit less than that at 94, still within one standard deviation, but a little bit lower. And then high blood levels are also at 94. So my suspicion is that there's going to be a significant difference between this guy and this guy and this guy and this guy, but not this guy and this guy. So let's go test. First, we check Levene's, and we see that we do not want a significant finding here, and we don't have it, so we are equal variances. So we've met that assumption, which is good. Then we go to our ANOVA table, and we look over here for our significance, and so our omnibus, our overall test, is yes, it is significant. There is a difference. Now we're going to check where the difference is. So we come to this multiple comparisons, and we're looking at the LSD, least significant difference, and this is how you read it. You go low blood level to medium blood level, you come across, yep, significant difference. Low blood level, high blood level, come across, yep, significant difference. But now we need to check medium and high. So we go medium and high, and we come across and we say, nope, not significant, which is just what we thought. When we look at the means plot, you can see a visual representation. These guys are at the same level. This one is different than that one. This one is different than that one, but this one is not different than that one. All right, so now we come to the effect size. We're no longer doing Cohen's. We're no longer doing Hedges. We're looking at eta squared, which is a Greek letter. And you don't have to go find this Greek letter. You can just write it out as eta squared. And the way we find it is straight from output. We just look at the sum of squares between. So not the mean square, the sum of squares. We get this top one over the total. So we do 20227 divided by 31336. I could have done it to the decimal place. I was just being lazy. And I get 0.064 or 6.4%. Now the way we interpret this one is different than Cohen's and Hedges, where we just had 0.2, 0.5, and 0.8, and we said low, medium, and high. Now this is actually a proportion. So we would write it out as 6.4% of the variation or variance in the dependent variable, here IQ, can be attributed to the independent variable, which is the measured level of lead in their blood. There is a significant difference in IQ in children among 3 levels of lead in the blood, or however you want to phrase it. That's a little bit awkward, but we'll do it that way. So we say the F of the degrees of freedom of the numerator, 2, right, over the degrees of freedom of the denominator, 118, is equal to 4.07, which I get from right here. P is equal to 0.02, which I get right here. And then eta squared is what I calculated. I got 0.064 or 0.064. And then I say a least significant difference post hoc test was conducted, and it was determined that there is a significant difference between the low group and both the medium and high groups, but no difference between the medium and high group. Okay. Now we're going to two-way ANOVA, factorial ANOVA. What is it and why do we do it? So a two-way ANOVA compares the mean differences between groups that have been split on two independent variables called factors. The primary purpose of a two-way ANOVA is to understand if there is an interaction between the two independent variables on the dependent variable. So let's look at an example on page 547. So we have females and males, and then they've grouped them by age, right? So we have a 2 by 3 factorial ANOVA. And inside these are the averages for this group. Females in this 18 to 29 age bracket have a pulse rate on average of 80.4. Males have an average of 64.8, right? So we see 80 and 64, 82 and 76, and 80 and 67. We want to know, is there a difference in gender, or is there a difference in age group, or is it a combination thereof? So IV1 is gender, 2 levels, and IV number 2 is age, and that's 3 levels, and our dependent variable is the pulse rate, which is continuous. So we have to look, before we can do anything else, we have to look and see if there's an interaction, so we would see the interaction if these lines were parallel. I did this as an SPSS, and there's a graph very similar to this in the book. So if there's no interaction effect, you would see these lines would be almost parallel. That would mean that the different categories of the variable have the same effect for the different categories of the other variable. So if this were high for the females in this group, then it would be high for the females in this group, it would be high for the females in this group. And I'm kind of seeing that, right? I'm seeing like there's not really an interaction effect, but this one might be the kicker. This might be the one that means there's an interaction. But when we have that, we have an interaction effect. So we have to look at that one first. So we have always, as always, assumptions. This is from page 548. We assume that they're normal. We have equals and variances, simple random sample, independent of each other. At least two ways. We have two categories for each outcome. And then we want balanced equal groups for this. It's very important that we have similar sample sizes. If we have vastly different sample sizes, our results are suspect. Okay, so we've got our data entered. We've got pulse rate, age group, and gender, right? And this one has, age group has 3 levels and gender has 2 levels. Using the data we've entered, let's use a two-way ANOVA to see if there's an interaction effect first, an effect for gender row and for age bracket column. So we want to look at the interaction and then the main effects for gender and age bracket. Use alpha is equal to 0.05. So first we have two hypotheses, that there's no interaction effect, then that there's no main effect. Okay, so we go to analyze general linear model univariate, move our variables over. So we're no longer using this compare means, we're using general linear model univariate, move our variables over. First, we're going to collect plots, then we're going to click post hoc, then we're going to do options, okay? And I'll walk you through each one separately. So plots. Here we have to think a little bit. Which would we like to see separate lines for? There are the age groups of the genders. I would think gender, so I put gender in the separate lines box, and then I put age group up here. So first I move age group, second I move gender, third, I click this add, and then it brings me over here, and it shows me this is testing the interaction. Age group times gender, right? And everything else we leave alone. We click OK, continue. Now we go back to that original, to this, it brings us back here, and now we're on post hoc. Okay, so we go to post hoc. Our only variable with more than 2 groups is the age group variable. So we want to do multiple comparisons for this variable, and we'll select the LSD, right? If we brought gender over, it would just kick it out and say there's only 2 groups there. So we move age group over, select LSD, hit continue, and now we're in options. We want to check descriptives, estimates of effect size, and homogeneity tests. So this one's going to give us Levine's, this is going to give us descriptive statistics, and then this one will give us an estimate of effect size. Finally, SPSS will do it for us and we don't have to calculate ourselves. Then we get to continue, and then we say okay. So let's take a look at our descriptives. We saw this already, right? This is the same thing I showed you in that first table with the 2x3, but now the computer has done it for us. Looking at the means, we can see our trends. Looks like the young women in every category have higher pulse rates than the men, but are they significantly different? Meaning, would we have found this by chance, or is it a real thing? So let's check our assumptions. Here, we actually fail the assumption of homogeneity of variance. And in the homework, I want you to just keep on going, even if you fail assumptions, so you can just go through the whole process. But we would state it in our limitations. We could just say, you know, it met the assumption if we based it on trim mean, so we're going to keep going. And then we'll just let our reader decide whether or not they believe us. All right, so now we want to just quickly check the abnormality. I would go back to analyze. I'd go to descriptives and explore, bring my DV over, bring my 2 IVs over. We get 2 different sets of normality because one's for the age group and one's for the gender. You can see that none of these are significant, so we have normally distributed data. All right, so let's go back, and you'd have to scroll back up in your output and look at the tests of between subjects effects. Actually, probably I would have done the normality before I started the general linear model routine, but that's not how I did it in the PowerPoint. If it's not, then we keep going. And in your homework, I want you to do that as well. If the interaction is significant, you can stop there and just say we have a significant interaction. So first thing we say is check is that the effect that the independent variable times this independent variable 1, which is our age group, times the independent variable 2, which is gender. We see it's not significant, so we can move to the main effects. Caution, the last column is the effect size and not the sig. So sometimes I get messed up. I'll come here and look at this as though I'm looking for the significance, and I'll say, oh, look at sig, but actually this is the column. So when you ask for that effect size, it's nice, it does it for you, but just be careful you're not looking at this for significance. All right, so the interaction's not significant, so now we're going to go and look for the main effects of gender and age group. All right, so age group, we come across, it's not significant. So it doesn't matter. There's no difference between men and women across the different age groups. Even though it looked like men might, in that middle bracket, might have been close to women, it wasn't significant. That interaction effect was not significant. All right? So what that means is pulse rates are the same regardless of age across the categories of male and female. All right? And then we see that there is a difference in pulse rates by gender. So there is a significant difference across gender. So the females were significantly higher than the males in each of those 3 categories, right? So there is a significance for gender, but not for age, and not for age times gender. So when we look at the multiple comparisons, given that there was that this was not a significant main effect, it doesn't make sense to evaluate these, since these will sometimes be significant even if the main effect is not. So, like, remember, the main effect of age group was not significant, so we don't need to check to see where the difference was. We just ignore it. All right, and then we'll write up our results. Okay, so now we have a little bit more to say. We have to write up our results. Okay, you can just copy this straight from the PowerPoint and pop it into your homework and then change the numbers. It's fine, and the variables. So a 2-way analysis of variance was conducted to examine the effects of gender and age group on pulse rates. Normality was assessed using Shapiro-Wilkes normality test for each cell of the design, and homogeneity of variances was assessed by the Levine's test using the summed means, or if your regular means are significant, then you'll use that one. All right, so the way we write this up is a little bit different because here we use the numerator and then the error term. So it says degrees of freedom for the numerator and then the degrees of freedom for the error. Let me go back and show you. Here, let me do it in the age group. All right, so the numerator is the degrees of freedom for the age group, and then the degrees of freedom for the denominator is the error term, 54. Okay? And then the other one would be 1 and 54. Okay, so the interaction between gender and age group on pulse rates was not significant. F of 2 times 54 is equal to 0.0, actually, so the first one we're reporting is this one. That's this 0.939. I just don't want you to get confused. Okay, so the interaction was not significant, 254.939, p is equal to 0.39, partial eta squared. Now this is the last we did eta squared, now it's partial eta squared. And you can just write it out. Therefore, an analysis of simple main effects for age group and gender was examined. There was not a statistically significant difference in mean pulse rates by age group, and I report those numbers, but there is for gender, and I report those numbers. This suggests that the pulse rates are the same across age group, but not across gender. That is how you do it.